I want to take a minute and work through some of these problems in the review section at the end of chapter 15, in particular page 1120, and help you get ready for the final. So we've got this line integral, number 21 I'll start with, and this is a line integral involving a scalar function. And what we're wanting to do is demonstrate that we know how to read what this is asking for. And that starts by realizing that we're taking this line integral over a curve, okay, right here. And this particular curve is a line segment that goes from 0, 0 to 3, 4. So here's what we need to do. We need to realize, okay, that's what this little c means. I'm going to evaluate this integral over that little curve. And we need to know also what d little s means. Well, d little s is going to be the magnitude. So if we find a curve, okay, so let's suppose I find the curve. It's got an x-coordinate, a function of t, and a y-coordinate, the function of t. And I've got this thing. Well, what ds is, it's the magnitude of the derivative of that vector-valued function. It's the magnitude of the derivative. So, in particular, here we've got this path, and we've got r of t, and it's a line segment. It starts at 0, 0 and goes to 3, 4. Well, if I just put 3t, 4t, and have t go from 0 to 1, that will do it. That's a line segment that, does that. Goes from 0, 0 to 3, 4. Now, we go ahead and set up the integral. So here's what we've got. We start at 0, and we go to 1. In place of x, I'm going to put 3t. In place of y, I'm going to put 4t. Now, I need to find ds. Well, r prime of t is 3, 4. Now, the magnitude of r prime is going to be the square root of 25. So I can put that here, 5 dt. And now we're right there at the end. We've got the integral from 0 to 1 of 25t squared. So this is going to be 125t squared dt. And if we evaluate that, that's going to give us 125 over 3. So, like I say, it's a matter of knowing how to read what the problem is asking for. Now, we've got a different path. Same integral, x squared plus y squared, but now we're taking a different path. Our path is a circle going counterclockwise, starting at 1, 0. So the way we can, there's a straightforward way to set up parametricize that. We could just say r of t is equal to, cosine t, sine t, because the radius is 1. If the radius had been 4, we would say 4 cosine t, 4 sine t, and so forth. Now, this will give you a counterclockwise rotation. If we wanted a clockwise rotation, we could use x to be sine and y to be cosine, but that one starts at 0, 1. So we have to be careful. But anyway, what I need now is I need the derivative. And that is going to give us, let's see here, we've got, hang on. We've got negative sine t, cosine t. Now I need the magnitude of that, which is going to be the square root, that's going to be sine squared t plus cosine squared t. And that's just 1. Okay, now one of the things I forgot to mention here is our t for one revolution is going to go from 0 to 2 pi. So we have to be sure we we don't forget that. So here's my integral. I'm replacing x with cosine, so that's cosine squared t plus sine squared t. And then this thing is just dt. So this integral turns out nice. 0 to 2 pi of just dt, which that's just going to give us 2 pi. So there we have it. Okay, now let's jump down here to another one, number 25. We've got a line integral, and our path here, the c, it goes from, it's a line segment from 0, 0 to 3, negative 3. So let's see if we can figure that out. So we'll have our path. Let's see. I guess this is just going to be 3t, negative 3t. See? So, and t goes from 0 to 1. So if I put a 0 in here, I get 0, 0. If I put a 1 in here, I get 3 now. Yeah, perfect. So all we need to do now is plug in, and we're going from 0 to 1. I've got 2x, so this is going to be 6t minus, and by the way this integral is set up, well, I'll tell you what, it doesn't matter. I start to say something, but I'll just go on with this. So we've got 2x, so that's 2 times 3t. Yep, that's 6t. And then minus y, so that's going to be a plus 3y. Okay? Times dx. Now dx is 3. Okay? Now let's see what else we have here. We have x. Okay? So the x is 3t. Y is 2. Y, well, we have 2y, and that's y is negative 3t. So that's negative 6t. And dy is negative 3. And all this dt. I should have put the dt over here. I saved it for the end. This is 3 dt, and that's negative 3 dt. But here, it all worked out. So now let's see what we've got here. We've got 0 to 1, and we've got 18t. Oh, I've still got a y in there, don't I? Let's see here. So this is y. This is plus 3t. And this is times 3. Yeah. So that's 18t plus 9t, and then minus 9t plus 18t dt. And there we go. So we continue from there, and you would end up integrating 36t, which would give you, let's see here, this is going to be 18t squared from 0 to 1. Yeah, so you just get 18 on that. Ran out of space here. I had to do a little bit in my head. Now, let's go down here and look at another path that we could take. So now we're going from 0 to 2 pi. Our integral is going to be 0 to 2 pi, just like before. And we're going to, or just like, a problem, the previous problem before, I guess it was, just like 21. 21 part B. There we go. Okay. Now we've got, this time we've got x equals 3 cosine t. So all we do is plug in here. So we've got 2 times 3 cosine t. Okay. Minus 3 sine t. Okay. And then times dx, which is negative 3 sine t dt. See, I just put in all the parts. And then plus, running out of room, so we've got 3 cosine t plus 6 sine t. See, just plugging in there 2 times y times dy dt. So that's going to be 3 cosine t dt. All of that is in this integral. Whoops. Okay, and then we would just work that out, and it's just a matter of now doing the algebra, just distributing through, and you'll come out with the integral. But that's the setup. Okay, now let's jump down here to number 29. Here we're asking for the lateral surface area over a curve C in the xy plane and under a surface. Now, when we first talked about integrals, line integrals for scalar functions, this is how we motivated it. We talked about it being the surface area. So we've got this curve, f of xy, and we've got c equals y equals 2x. Now, of course, we're going to, we've got this situation. This is the type of integral that we're thinking about. And if we want to come up with a parameterization for that curve, we could just do this. We could say, well, let x be t and let y be 2t. And then we've got, and we could just go from, and now remember, we're going from 0, 0 to 2, 4. So notice if t is 0, we get 0, 0, 0. And if t is 1, we get, that would give us 1, 2. Well, we want 2, 4, so I better make that t goes from 0 to 2. Okay, so 0 to 2. So we get that set up first. And then I just say, okay, the derivative is going to be 1, 2, and the magnitude of that is the square root of 5. So here's what we've got now. We've got 3 plus sine t plus 2t. That's 3t. And in place of ds, I'm going to put the square root of 5 dt. And we just integrate that. Okay, now let's move along here. Okay, now we've got a vector field line integral. So a line integral involving a vector field. And now, so let's see what we've got. And we've got a curve here. They went ahead and gave us the curve. See? So they gave us r of t is equal to t squared, comma t squared from 0 to 1. Okay, so let's see how this would work. We've got our vector field. Okay, so here we go. We've got xy, comma 2xy. And we're dotting that with the derivative. So look, this is going to be 2t. Go ahead and put the dt in there. And we're going from 0 to 1. Now, I've still got x and y in here, so we'll have to keep going now. So I've got 2xyt. Well, no, I don't either. I've got 4. No, yeah, I had it right. I was looking at, okay, so we've got 2xyt plus 4xyt. I was looking at this one a minute ago. Okay. And dt. Okay, so I did the dot product. Now what I've got to do is I've got to plug in the x and the y. So this is going to be 2t squared t plus 4t squared t dt. And that will give us the integral from 0 to 1 of 6 t to the 5th, which is the integral, we'll go ahead and integrate it. This is going to be t to the 6th from 0 to 1, which is 1. Okay, now let's move along. Go down here to 33, and we'll look at a line integral for a vector field with 3 components. Okay, so remember, it's the same process. What I need to do is I need to get the derivative. Okay, so here it goes. This is going to be negative 2 sine t, 2 cosine t, and 1. And now I want to dot product these two. So I've got x, y, and z, and I'm going to dot product it with this derivative. Okay, so if I dot product, here's what I get. I get negative 2x sine t plus 2y cosine t plus z. Yeah, we're just dot producting. Now I can replace the x with 2 cosine t. So this is going to be negative 2 cosine t. Actually, the x is, we've got some extra things in here. Notice the x is negative 2. So here's what I'm going to have. I have negative 2 times 2 cosine t times sine t. Okay, so that takes care of this first one. This is negative 2x t, okay, plus 2, let's see what y is. Y is 2 sine t. Okay, so 2 sine t cosine t plus z, and z is equal to t. Okay, so let's just make sure we got everything right. 2 cosine t, I put that in place of x. Okay, 2 sine t, I put that in place of y. Okay, and then in place of t, I put in place of z, I put a t. Yeah, good. Now this is what we're going to integrate. We're going to integrate this from 0 to 2 pi. So here's what we've got. We've got negative 4 sine t cosine t plus 4 sine t cosine t plus t. And it looks like what we've got then is just we've got 0 to 2 pi t dt. Okay, so that's a simple one to integrate. We just have 1/2 t squared from 0 to 2 pi. So that's going to be 4 pi squared divided by 2, which is 2 pi squared. Yeah, that's all there is to that one. Okay, now let's look at 35. 35, the interesting thing about this problem is they give you the curve to be a curve of intersection of a couple of surfaces. You've got z equals x squared plus y squared, this paraboloid, and then you've got this plane, y equals x. So we need to find the point of intersection, or the curve of intersection. So let's just do this. Here I've got z is equal to x squared plus y squared. But you know, y is equal to x, so this is x squared plus x squared. So z is equal to 2x squared. So let's do this. Let's do r of t is equal to x, let's call that t. Y, it's the same thing, it's t. But then z is 2t squared. Okay, now let's see how this works. We're going from 0, 0, 0 to 2, 2, 8. So I'm going to have t starting at 0. And let's see here. If I have t going to 2, let's see if that will work. We get 2, 2. Yeah, that will work. 2 times 4 is 8. Yeah. So this is what I want to use. So let's see what we've got here. Here is the function, here is the vector field, f of x, y, z. So y is, so we've got y plus z. See, y plus z, that's going to be t plus 2t squared. Okay? And then we've got x plus z, so that's going to be t plus 2t squared. And then we've got x plus y. That's just t plus t. Okay? So this is f of, x of t, y of t, z of t. That's what this is. Okay, now I'm going to dot this with the derivative. Now, so the derivative is 1, 1, 4t. So 1, 1, 4t. And this is going to be what we're going to integrate. So let's see here. We've got t plus 2t squared plus t plus 2t squared plus, this is 2t, that's going to be 8t squared. So let's see what we've got here. We've got 2t, add like terms, and there's 2, 4, that's going to be, I guess, 12t squared. And there, all we do now is we put that in our integral. Our bounds are 0 to 2. We've got 2t plus 2t, well, 2t plus 12t squared. And then, we just integrate that, and we get t squared plus 4t cubed from 0 to 2. So that's going to be 4 plus 16. Actually, not 16. This is going to be a 4 plus 8 times 4 is 32, so that'd be 36. There we go. Okay, now, so we've just been using, just addressing these line integrals, not using any theorems or anything. But we have been given a few theorems. One of the first ones, the very first theorem, was the fundamental theorem of calculus and for line integrals. So we learned that if we have a line integral that is for a vector field that is conservative, then we can use the fundamental theorem of calculus. Now, we've got this vector field. Let's look at this vector field here. We've got 2xyz. We've got x squared z. And we've got x squared y. Now, if this vector field is conservative, in other words, if this is someone's gradient, then we can find that potential function, okay, the function that we take the gradient of, and we can just use the fundamental theorem. We can plug in this point minus this point. So let's see if it is conservative. So let's take the curl. Let's take the curl of this function. This is how we find out. I, j, k. Okay, so we've got partial with respect to x, partial with respect to y, and partial with respect to z. And then we've got 2xyz, x squared z, and x squared y. Okay, so let's see what happens here. Okay, we've got this first one is going to be x squared minus x squared. Okay, so this first one is 0. This first coordinate is 0. Now remember, we want all three of these coordinates to be 0. We want this to be the 0 vector. Okay, so let's look at the next one. This is going to be we have 2xy minus 2xy. Okay, good, that's 0. And then finally, the last one, this is going to be 2xz minus 2xz. So this does indeed equal it's the 0 vector. So that tells us that I need to find the potential function, and then I can just plug in. Okay, so let's see if I can find the potential function. Let me just integrate. I'm going to say, okay, this function fyz is equal to the integral of 2xyz dx. I'm going to integrate with respect to x. And when I do that, I get x squared yz plus some function of y and z. Okay. But notice the partial with respect to x is 2xyz. Now, the partial, let's see, maybe this is enough. Maybe the potential function is x squared y and z. Maybe we don't have to go any further. The partial with respect to x is 2xyz. Now, the partial with respect to y, well, it's x squared y. Partial with respect to z, is x squared y. So we have it right here. We don't have to figure out what this thing is. Our potential function is x squared y and z. So this thing is just x squared yz going from 0, 0, 0 to 1, 3, 2. So all we have to do is plug in 1 squared times 3 times 2 minus 0. So it looks like that's going to be 6. Okay, so let's move along. Now the next theorem that we were given was Green's theorem. And Green's theorem, remember, you're dealing with a closed curve that's oriented counterclockwise. Okay, so it has to be that. It has to be closed and oriented counterclockwise. In other words, if you're walking around the curve, the area is on your left. Now, so here's what we do. For Green's theorem, so we've got this vector field. And in this case, it's y, 2x. And what we want to do is we want to take dn with respect to x minus dm with respect to y. Okay? And what we do is we set up a double integral with this. Okay? So we have partial with respect to partial of n with respect to x, minus the partial of m with respect to y. And we want to integrate that over this region. In this case, we're going to integrate over the xy region in the xy plane. So here's what we've got then. We've got this double integral, and I'm going to take the partial of n with respect to x, which is 2, minus the partial of m with respect to y, so that's 1, over this region. And of course, this turns out to be, nice. We've got, now we're just integrating over this square. So we're going to go from 0 to 1, 0 to 1 for x and y. And this is just going to be, the area is just dx, dy. So that one turns out to be really nice. Okay. So that is, I think this is number 45. forgot to put the number in that I was working. And I think that previous problem, let me look and see what that one was. I think that was problem number 41 in your book. It seems like I forgot to list these problems. Okay, there we go. There's 45. Now let's look at 47. It's another Green's theorem problem. And notice we've got a circle. This one, our curve is a closed circle going from 0 to 2 pi. So we'll use Green's theorem here. So here we go. We need to find partial of n with respect to x minus the partial of m with respect to y. So let's see what that's going to be. And our function, let's just look at this vector field. We've got xy squared, x squared y. Okay, so partial of n with respect to x is going to be 2xy minus partial of m with respect to y, and that would be 2xy. 0. So we tried to use Green's theorem on this one, and we just get 0. So this makes the problem super easy for us. Now, look, what that tells us is that this vector field, xy squared, is conservative. So when you integrate a conservative vector field over a closed interval like that, you're going to get 0. Okay, so let's see what's next. Ooh, that's the last problem I had written down. I'm going to post these videos, or this video, and then I'm going to work a few surface integral problems. But I'll just post these for now.